This is a joint work with actually with Michael, Binyu, and several junior faculty and my students. Okay, so essentially this is this is the setup of this my model. Okay, so essentially it's a linear regression model, very simple, and then we're talking about a tau matrix, and Y is the response, and this is a predictor matrix. And then these are the coefficients, and then we have a residual. And for simplification of presentation, and then we simply assume this error is random error is IID normal distributed with mean 0 and the variance equals sigma square. Okay, so the key point of this randomized numerical linear algebra essentially is just take a subsample from this full sample. And then in linear regression, there are two purposes. Okay? The first purpose is if we wonder whether we can take a subsample so that this using this subsample for the computation so that we can well approximate a full sample least square. Okay? That is this is using full sample. We use beta height OLS to denote this is a full sample OLS. But in linear regression analysis, we know that this full sample OLS, what is useful? It's useful to make an inference to the underlying true coefficient beta 0. Okay, so then this subsample estimator can be also used to make an inference on this true underlying coefficient. So we have dual purpose. One purpose is to approximating this full sample OLS. The other purpose is to estimating the underlying true coefficients. Okay. So then there are in statistics, when we talk about random sampling, typically we are talking about uniform random sampling. And here I put a simple example to illustrate uniform random sampling may not work very well. So I generate 2,000 data points from a simple linear regression with only slope and intercept, and then the plot, all the points form a cloud point here, and then we randomly take 10 data points from these 2,000 data points. Okay, and using uniform distribution, and then in a single run, I got these 10 points. I use green star to indicate them. And then,
what's the dimension of your matrix?
Oh, my matrix is only 2 dimension, so it's only has intercept and has slope.
So it has 2 columns.
Yeah, only 2 columns. Okay.
How long?
There are 2,000 data points. Okay. Yeah. So I generated 10. I sampled 10 data points, and then I using these 10 data points, I fit a line, and this is this blue dashed line, and you can see it's very far away from the true regression line I generated data. This is the black line is the line I generated data. And if I use all the data points, 2,000 data points, to fit least square regression, actually I get another black dashed line, but hard to visualize, almost identical with the true regression line I generated data. Okay, this spell out that these uniform random sampling may not work in some situation. Okay, so why it doesn't work? If we look at these data clouds, we find most of the data actually in these data clouds, but the so-called critical or influential data points are actually located in this edge. Okay, there are several data points here and several data points here. These are more influential data points. Okay. And in 2-dimensional data plots, obviously, we can easily identify which data points are influential. But mathematically, we need a formula to characterize how to characterize the influential measure of the data points. Okay. Yes.
So you said that the data is 2-dimensional. So both of these dimensions are the input dimensions, or is one of these dimensions the
data are 2-dimensional with only slope and the intercept. Okay.
I think the matrix is the input, the matrix with 2 columns.
Yeah, just 2 columns.
So the vertical axis has the label.
I see. So the x-axis sort of represents both dimensions, or like one of the dimensions of the data.
Yeah, this is one dimension. This is, y-axis is another dimension. And then this is the data point, where the data point is located. Okay? Okay. So, and then we need some measure to measure the influential. Okay? Mathematically, this can be done using this perturbation concept. Essentially, we say this is my least square regression line, okay, for the particular prediction for ith data point, okay? And then I say that let the real data point perturb a little bit and how much these will change, okay? These can be used to characterize the influential, or how influential a data point is.
Is that a partial derivative?
What?
Is that a partial derivative?
It is a partial derivative in terms of this could be
So what are you differentiating with them?
with respect to the true data
So how do
point,
you know
yi.
it's differentiable?
Okay, let me show you in the next slide. Okay, so how these things apply to our case? Essentially, in the least square regression, okay, we can show that this least square regression can be written as a linear combination of the observations. Okay, and then in statistical analysis of least square regression, we assume all these X matrices are fixed, okay, is non-random. Only Y is random, okay? And then in this case, very simply, we can write this as this format. These HII, essentially the elements of these so-called, we call so-called height matrix. Height matrix can be written as this format, X times X transpose, X inverse, X transpose, okay? So this is a height matrix. And then now, if I say, okay, it's not, if I say this is partial derivative, okay, here maybe more appropriate to use direct derivative. Okay, if I take a derivative, then it's exactly equal to this HII. Okay, so this is typical setup in statistics. Okay. And then how to calculate this Larry score? Then we use numerical linear algebra that is through the singular value decomposition of predictor matrix. And then we can easily show this HII, this is so-called Larry score, essentially equals the row square norm of the left singular vector matrix. Okay, so this is the Larry score. And then so now we say these leverage or indicate these the influential measure, and then using this intuition, and then we basically have this so-called basic leveraging algorithm. Okay, so that is take this leverage proportional to our sampling probability, and then using this sampling probability to get a subsample, and then we get our leverage estimator using weighted estimate of these least squares. Okay, so this is essentially the basic leveraging estimate. Okay, and then so back to our toy example. So this still these 2,000 data points, and then we run this basic leveraging algorithm. We can see we select 10 data points, and we can, because this is a random algorithm, we can see some edge point being selected, but some also data points in the data class also being selected. And then using these 10 data points, we fit this least square line. This is the right line shown here. It seems much better than this regression line using uniform sampling, but still has a little bit of bias with respect to the true least square line I generated, the regression line I generated the data. Okay. So this is intuition behind this basic leveraging estimate. Okay. So the next thing, as I said, okay, we have two purposes for this leveraging estimate. One purpose is to approximating these full sample least squares. Another purpose is to make an inference or estimate the underlying true parameter. Suppose we assume there is a true parameter here. Okay. The true value of this parameter. Okay. So, but there are some difficulty. There is a significant analytical difficulty. Is this leveraging estimate can be written in this format? Essentially, this is a weight matrix W here, But this weight matrix is random because we sampling this. But this leveraging estimate depend on these through a nonlinear function. So these make analytics really difficult to work with. Okay.
Why does that inverse exist?
So this is a least square.
But why does the inverse exist? The sampled matrix isn't necessarily full rank.
Right. Okay. Assume this is a full rank. Okay. Let's make things simple. Yes. You can have a very great point. Okay. If this is not full rank, then this needs to be generalized inverse. But let's assume. Okay. After subsample, this is still full rank. Okay. We can take a regular inverse and then get this. Yes, please.
Excuse me. So you are doing sampling. The sampling matrix W as a function of your Y, right? So the random W kind of depends on Y, if I understand correctly.
Right. Yes. These basically this beta depend on Y. Y here there are two randomness. One is Y. Y is random. Okay. X matrix is fixed.
Yes.
And then but this W, this sampling matrix is random. Yes.
The sampled rows of X
Independent
and
of Y.
Yeah.
Yeah.
Okay.
Independent.
If you
Yeah.
say
Without considering Y.
17th row of
Yeah, I
Y,
agree, but there's I have intuition that he's kind of weighting the observation.
No, he's constructing the probabilities from the matrix X by using the leverage scores of X. Those are the probabilities he's using for the sampling.
Okay,
Right.
okay, I see.
Yes. If we depend on Y, these things will be much more complicated. So it's kind of right now we are sampling independent of Y. Only look at the X matrix itself. Okay. Good. So. Okay. So then in 2014, we have a paper essentially try to do some analytics. So we write down what it is really is. Okay, for this sampling matrix, essentially it's a multinomial distribution which each sampling probability. Okay, and then the next thing is how can we analyze it? Okay, one simple way of doing this is through Taylor expansion. But this Taylor expansion is with respect to random coefficient. Okay, so we think we treat this leveraging estimate as a function of these sampling weights. But this sampling weights is random, and then we just expanded using Taylor expansion. We got this constant term and the first order term, and we essentially ignore the residual. We assume the residual is well controlled.
Taylor expansion exists, that residual term is small. How do you know that?
Yes, that's a good question. Okay, whether this residual could be well controlled is another critical question. Okay, so this is the reason I want to present my result. Okay, in the few slides. Just hold on for a few minutes. Okay, so this is just a very rough estimate. Okay, using Taylor expansion, let's assume this is well controlled. At least we get some idea. Okay, what this look like the first few order of Taylor expansion. What does it look like? And using these analytic tools, essentially we can get something about these bias and the variance. Okay, we get two kind of conclusion. The first we call the conditional analysis. Conditional analysis, essentially we said, let's treat this data being fixed. Okay, data is being given. Our idea is really want to approximate these full sample least squares. Okay, if this is the case, then this is what we get. So expectation of this given the data will approximately equal the full sample least square with some residual term. Okay.
Excuse me, I'm really sorry to interrupt so often, but if your sampled matrix is full rank, then as I showed yesterday, what you get that beta tilde is an unbiased estimator. You don't have anything else. If the sketched matrix is full rank, which is what you're assuming.
With respect, okay, here, okay, there are two things. Let me say, okay, there are two things. Okay, one purpose is we approximate full sample least squares. Another is to estimate underlying true coefficient. If your purpose is to estimate underlying true parameters, then yes, okay, you get an unbiased estimate. But if you do in this approximating full sample least squares, then you could end up with a little bit of bias here. Okay, there are some conditions.
Yes, yes.
Okay.
If the sketch matrix has full rank.
No, but he conditions on Y.
Even full rank, I don't think that you can
Yes.
remove the bias. Maybe with some extra conditions. Okay.
Oh.
Then we can discuss offline. Okay. So because right now, at least we
You have a
already
fixed sampling matrix, a fixed W, right?
W is random.
Are you conditioning on all? So what are the expectations?
I
of variance
conditional on data, but I didn't conditional on weight.
So the expectations of all weight matrices.
With respect, given the data. Okay. This is a typical route in statistical analysis. Okay, so we can discuss offline. Okay, here is essentially this, and then this is the variance. But once again, if you are interested in estimating the underlying true coefficient, then yes, you get the unbiased estimate, and then you get this variance, and it's complicated. Okay, and the things is here. Okay. All these terms, okay, the higher residual terms, we say there are some residual terms. Suppose they are well controlled, then we can only look at the first few orders. But the thing is we didn't provide any precise statement, okay, how this residual can be well controlled, okay? So next thing is because this expression is complicated, so we want to somehow simplify these expression to get some well and nice operatable expressions. One way of doing this in statistics is through this asymptotic analysis. Asymptotic analysis is a long-standing practice in statistics. Okay, so essentially, it can simplify this complicated expression, and many times can give us very nice workable solutions. Okay, so what we did is the following. The first thing is so-called unconditional asymptotic analysis. Okay, essentially under two regularity conditions. I didn't present here, but it's really very minimum. It's the design matrix essentially need to be satisfy certain condition, moment condition, and then sampling matrix you cannot have zero as long as it's not too small. Okay, then we show this leveraging estimate. Okay, asymptotically converts to these underlying true parameter beta 0 with certain covariance structure. Okay, and this covariance structure can be very nicely written in this format. This omega is just this 1/r is our subsample size, and then pi I is each data point's sampling probability. Okay, so essentially this statement tells us this so-called asymptotic expectation of this leveraging estimate equals to the beta 0. Okay, the underlying the true value of the underlying coefficient, and then the asymptotic variance equals this V0. Okay, present here. Okay, so this is essentially this asymptotic analysis. Okay, and then using this, we can combine these two. Okay, combine these two, the expectation and then variance. We can get asymptotic mean square error. Okay, and but there are several asymptotic mean square error we can get. Okay. The first thing is if our interest is to estimating this beta 0, that is true value of this underlying coefficient, and then we got this asymptotic mean square error have this expression, and then if we want to minimize this asymptotic mean square error, we will end up with this sampling probability like this. Yes?
To be clear, R is the number of subsamples or the number of original samples?
R is the subsample size. Okay, the subsample you take. N, little n is I use little n as original sample size.
So
yes.
previously we say as the number of subsamples approaches infinity, right?
Right.
So does that mean that simultaneously we're also taking the number of samples to go to infinity, right?
Okay. Yeah, so that's a good question. Okay, so these inference essentially already assume this n also goes to infinity. Okay, I forgot to put the condition. Essentially, this R must be a smaller order of n. Okay, sorry, because I didn't put the regularity conditions. It's too long. Okay, so essentially, R is a smaller order of this, and this statement can be say, okay, as long as n goes to infinity, that also implies R goes to the infinity. R goes to the infinity also implies n goes to the infinity, but n goes much faster than n, much in a higher order of R.
So can this characterize then sort of the relationship between the number of subsamples and number of samples needed? Like, what here can we say is nice because there's an infinite number of samples? What here can we say is nice because there's an infinite number of subsamples?
Yes, in a certain sense, okay, so if you can say, okay, this subsample must be a certain magnitude, in a lower magnitude of subsample, and then as long as this satisfied, and then these asymptotic analysis hold true, okay? But in terms, later on, there could be another question is, how do we select the subsample size? And then this will trigger another question, and then how precise your estimate is. And this is related to this asymptotic variance.
Analytically, is there any difference from having R and not having R in here? Because this essentially just becomes a least squares problem with infinite samples, right?
Right. This just make this statement complete. Okay. It's just without this R, with this R, you are right. Okay. It really doesn't matter too much here. Okay. Yes. Okay. So anyway, so essentially we got this estimate. This estimate I think is pretty. I didn't see anywhere. Okay. So this is basically this inverse of this X transpose X matrix times this observation, this I's observation of this X observation. Okay, so we can use this if we want to estimate this beta 0. Okay, and then another line of interest is instead of estimating this coefficient, we want to estimating the true regression line. Okay, that is this. X times beta 0, okay? If this is the case, we get another, this asymptotic mean square error now is X times this, and then you plug in this and simplify a lot of expression, and eventually, very interesting, we end up with this, and after simplification, we get this estimate, okay? We call this as the root leverage score, okay? So it's a square root, okay, for this. For estimating this will be the best. Okay. Okay. Yes.
Do you have an intuition why in the statistical analysis you get the square root of the leverage score rather than the leverage score?
Okay. So the intuition is once again this leverage score. In statistics, if you look at the standard textbook, okay, leverage score sometimes it also indicate this. If it has a very high value, indicate it could potentially to be an outlier, okay? And then by doing this essentially a nonlinear shrinkage, basically saying for quite large this leverage score one, I want to downweight it a little bit. Okay, now that's significant. And in those cases, then we have a chance to select this not very extreme high leverage data points. Okay, so it's kind of nonlinear shrinkage. Yes, go ahead.
For high leverage square like close to 1, it doesn't affect it very much, right? Because you go from like square root of something slightly less than 1.
Yeah, don't you want to upweight the small ones? Isn't that?
So it's the small ones that affects significantly.
Right, but high leverage also means square root, right?
But the highest the leverage is 1, right? So like.
I think later on I have a plot. Okay, hold on. Okay, and then I think that is a circle, and then you for the low leverage one you boost it up. Okay, for high leverage one you make it lower down.
Have you seen? I've seen also work where it suggested to do mix leverage score with uniform, right, which would have a similar effect of pushing up
Right.
small
Okay.
sample.
Hold on your question. Okay. And later on, I will show you that these we call the shrinkage leverage. Essentially, it's originally actually exactly suggested Michael. Okay. It's we mix these basic leverage score with these uniform random sampling and mix them together, and then it's really doing again. It's doing a linear shrinkage, but this is kind of a nonlinear shrinkage. Okay. Yes. Okay. So the next question is a little bit mathematical trick. Okay. So if we can do this, this essentially saying we can put any matrix, okay, before this beta 0, okay, and now instead of x, and I put x transpose x, okay, and then we get even more interesting estimator, okay. So if the interesting is doing this, okay, and then it's really simplify this expression quite a lot, and eventually we end up with a sampling probability of this we call the predictor length leveraging score. Okay, this is a sampling score. It's very simple to calculate, obviously, because you just using linear computational cost can calculate these costs. Okay.
Why would you be interested in this particular error?
Okay, so it's just to simplify some mathematical calculation. Okay, we put this and then we end up with this. We thought, okay, there could be some interpretation. Okay, so these could be interpreted as the true regression line, and then these the predictor. Okay, there are these inner product between them. Okay, yeah. Okay. So, but anyway, it's end up with this. Obviously, this is much simpler to calculate, but compared to the leverage score, it also the advantage is so clear. It's computational, so simple, so neat. Okay, but disadvantage is also has some significant disadvantage. That is, this is not if we have a certain transformation for this predictor matrix, this will change. Okay, but originally, if we do a simple transformation for the matrix, and our leverage scores still keep the same. Okay, so this is this basically says this is original leverage score is invariant to certain transformation, but this is not. Okay. Okay. So the next analysis is doing the conditional analysis. The so-called conditional analysis is that we keep the we keep the data fixed. This is a given, and then our goal is try to approximate these full sample least squares. Okay, using this, once again we get this asymptotic analysis, and this is our leveraging estimate. This is full sample least squares and with certain covariance matrix. And then this is basically say asymptotic expectation equals the full sample least squares and the asymptotic variance with certain variance structure. Okay. Here, only tricky part is this. Okay, is in this variance is a sandwich type of formula, and in the middle part of this expression actually involves some this E of EI, okay, which is a residual of the standard the full sample least squares. So essentially, this is YI, and you need to have the full sample least OLS first, and then using this minus this, and you get this. Okay, so then this makes things much harder to work with. Essentially, if we want to work with any of the variant calculating this asymptotic mean square error, so we need to have this, okay, in order to have this. So we make some trick. We calculate something so-called expectation of asymptotic mean square error. Essentially, we take another expectation after we get asymptotic mean square error. The basic idea is try to remove this EI out. Otherwise, it's very hard to calculate, because that means we need to first go to the full sample least square. Then the whole calculation just lose meaning. Okay, so then if we're doing this, we end up with some simple expression, and then eventually we end up with here the sampling probability. It's very surprising. Okay, sampling probability based is proportional to the square root of 1 minus HII. So if HII is higher, and actually these getting lower probability. But the intuition of this whole expression is these being compensated by these weighted predictor lines, okay, by this part, okay. So these are essentially if this is lower, this will be getting higher, okay. So this is if we are the purpose is to approximating these full sample OLS, okay, coefficients. And then the next thing is if we are interested in approximating the full sample least square line, okay, then we get another interesting expression. That is the square root of 1 minus HI times HI, okay. This is 1 minus this Lagrange score times the Lagrange score, okay. So this is basic beauty of this mathematical analysis. Sometimes gives you a little bit of surprise result, okay. So the third thing, analog to what we did for unconditional analysis, we can do this, okay. So then we eventually end up with the probability, sampling probability 1 minus HI times the predictor length, okay. So this is the sixth sampling probability we get from our asymptotic analysis. Okay, so I think, okay, so I plot a simple plot to try to give you some idea. Suppose this HII can be written in here when the X matrix is orthogonal, okay, is orthogonal to the column is orthogonal to each other, then this is our root Lagrange score because it's square root. And then look like this. This is basically for smaller Lagrange score, it's being pulled up, and then for this high Lagrange score, it's being pulled down. Okay, and then this. Oh, sorry, this is not a root. And this is this 1 minus HI times HI square root. Okay, so this is our estimate, and then this is this square root one. Okay, this is a square root one being. For smaller one being pulled up a little bit, for higher one actually pulled down a little bit. Okay, these should be look like this if I plot correct, if I make it a sum to 1. Okay, and then this is this so-called shrinkage Lagrange estimate. That is a linear combination of the regular Lagrange score and then with this regular uniform sampling probability. Okay, it's Lagrange like this, okay? So this is some of the intuition here, okay? So then once we have this asymptotic analysis, the beauty is once we used to this idea, and then this analysis can be applied to a wide variety of settings of analysis. For example, now let's take a look at the large sample classification problem. Okay, so suppose we have this is our response. Okay, but instead right now we say that these are our classification label. It's either 0 or 1, or in support vector machine you can also use a -1, +1 to indicate these are the two class label. Okay, and then in the large sample classification problem, there is quite a difficulty problem, so-called extreme imbalanced classification. So suppose one type of sample is extremely small. Okay, the other class is a majority of the class. So then the typical idea is you do this analysis using subsampling. Okay, but anyway. In this particular case, let's just focus on this so-called logistic regression, very simple setting. Okay, logistic regression essentially in statistics we assume this class label is 0, 1 follow this so-called Bernoulli distribution with a certain probability, and then the log odds ratio or log odds of this sampling probability equal a linear combination of these X predictor matrix. And then to fit this model to the data, typically we use the maximum likelihood estimate, okay, and then have this certain format. And once again, this is because this is a nonlinear function with respect to this beta coefficient. So the computational cost is NP squared with certain the iteration, how many iterations you have. We use this Greek letter to indicate, okay, there are some iteration, okay. So once again, we can use this general leveraging algorithm. That is, we take a subsample of size r with a certain probability pi I, and then once we get a subsample, we can use a weighted maximum likelihood and then to get the estimate. Okay. So once again, we resort to this asymptotic analysis. We can show that this leveraging estimate is asymptotically unbiased with respect to the full sample maximum likelihood estimate with certain variance structure. Okay, certain variance structure. But once again, we end up with some dilemma. That is, our asymptotic analysis actually this variance structure once again is a sandwich type of formula with the inner part depend on this sampling probability. But this sampling probability once again depend on the estimate of full sample MLE, okay, maximum likelihood estimate. So okay. Anyway, so eventually, with respect to minimizing this asymptotic mean square error, and then we end up one of the sampling estimate. We end up sampling probability. We end up with is something like this. Okay. So essentially, this is the predictor length. We just saw this. Okay. And this is another absolute value. Remember, in the context of the logistic regression, the y is either equal to 0 or 1. Okay? And this is the sampling probability. Essentially, here basically saying, okay, if this sampling probability is far away from either 0 or 1, okay, is deviate from 0 or 1, then this basically means that these data points is high likely to be misclassified. If it's misclassified, we need to give them higher sampling probability to sample them. But by compensate, you need to take these predictor lengths into account. Okay, so this is the sampling, the idea. Okay, and but in order to break this loop, because our sampling probability here, okay. Once again, in order to calculate this, we need to have this full sample MLE. Okay, so we end up with chicken egg problem. In order to break this loop, so we designed this two-step leveraging algorithm. Essentially, we take a subsample first. Okay, we call this sample size R0, and this is a uniform subsampling. For uniform subsampling, get a very rough estimate of this sample MLE, okay, full sample MLE, and then plug in and then calculate this sampling probability. And then once we get sampling probability, we take another sample, okay, and then take a weighted sample, and then follow this rest of the recipe of the leveraging algorithm. Okay, so this is the idea. Okay. I didn't show this simulation and all these things, but let me show you a real data example. Okay, this is a supersymmetric particle. Okay, this data we downloaded from UCI machine learning repository, and the original paper was published in Nature Communication, I think, in 2014. Okay, essentially there are 5 million observations, and this is roughly balanced data. 50% of the background events, and the other is the events we are interested. Okay, and the feature, there are only 18 features. They calculate certain velocity and so on and so forth. Okay, and what this original paper did is they use 4.5 million as training data, okay, and then they use 0.5 million data as test data to test their classification accuracy. So what we did, and then, this is original paper is published in 2014. Okay, what they did is they trained 5-layer neural networks and with 300 hidden units in each layer. Okay, and there is one phrase in the original paper which take us a lot of time to parse the meaning of this. They say that due to the computation cost, this optimization was not thorough. Okay, eventually we figure out what's going on. Essentially, at that time, 2014, training these 5-layer neural networks still takes a lot of time. And then for this particular work, they didn't finish the optimization. After run 1 month, they just stopped there and they said, okay, let's just make these look at the classification. Anyway, they use the GPU and the special software. There is a commercial software and whatever. And eventually, they report this something so-called area under the curve. Okay, so it's you calculate this ROC curve and then calculate this thing, and then they got 0.88. Okay, and what we did is this 0.88, and then there is no testing error. Okay, they just use a full 5 million data points, and then they report this. And what we did, okay, is we use 4.5 million as training, and then use 0.5 as the testing. And then for 4.5 million, and we only sampled 2,000 data points out. And then eventually we calculate ROC. Our ROC is 0.851. And also we have another slightly different sampling probability. We end up with similar these area under the curve. Okay, essentially our calculation only take about several minutes, and then their calculation take us a very, very long time. So these spell out. In sometimes these leveraging estimate could be a good method for pilot study for something you want to real quick. Okay, it could give you a very quick estimate. Okay, so this essentially everything we done, and this is joint work. We talked about this linear regression part is joint work with Binyi and Michael, and then the asymptotic part is Michael and with my students and Xinlian Zhang and Xing somewhere. Okay, here. And then for this logistic regression with this junior faculty, and then these and they support by several grants. That's all I want to talk about for today. Thank you.
Any other questions?
Yes.
So in the logistic regression part towards the end, whenever you came up with these sampling distributions, it looked like mostly based on the error in the row norms, right?
Yes, row norm, and also with this probability y minus this sampling probability.
So did you get anything that sort of feels like row norm sampling a little bit in linear regression, and less like leverage sampling, right? Was there any way to get something that looks or feels a bit more like leverage sampling? Or thinking about sort of how vectors compare to one another in some sense?
Right. So for logistic regression, the leverage is not well defined.
Okay.
Right. So there are several definitions of this leverage, and we first tried this leverage score. It seems doesn't work very well, so we just gave up and eventually end up with this more rigorous way, because leverage essentially is an intuitive way, but it doesn't give us a very rigorous framework. But we end up, we use this asymptotic analysis to guide us to select the sampling probability.
Okay.
Yeah. Thank you. Okay.
Oh, one other question.
Yes.
Yeah, so logistic regression doesn't have any closed form solution with respect to the MLE, right? Of the
Say again, I didn't quite.
So there is no closed form solution of the beta, right, for logistic regression?
Right. There is no closed form.
So what is the leverage score estimate of beta in that case?
There is no closed form. There is no closed form. So this reason we did several steps.
You just sampled the rows and then again compute that iteratively reweighted least square.
Yeah, so we essentially we say that this is just this nonlinear optimization solution. There is no closed form to say. Okay.